So having proved Banach's fixed point theorem in the previous video, we'll now move on to the proof of the inverse function theorem. Even to state that theorem requires a little bit of language, so let me get started with that. So, well, we have our Banach spaces as usual, V, W with their norms. Well, U, U0, U1, or U, U0, U1, they're all going to be open subsets of V, V0. And let me start with the definition. Well, a function f from an open subset of V to W is C alpha. Alpha here is an integer, positive integer. If f is alpha times differentiable, and moreover the derivative of order alpha, well, remember, to each point in U, it associates alpha linear operator from V to W. So, and we're assuming, when we say that f is C alpha, that this mapping here is continuous. So the mapping that takes x to d alpha f of x is continuous. Now, there's a stronger concept, which is I have two subsets, in this case of V, though I could also talk about more general Banach spaces, but let's stick with V here. So a mapping from an open set of V to another open set of V is a C alpha diffeomorphism if it's C alpha, so has alpha derivatives, all continuous, and moreover it's a bijection. So there's an inverse mapping, right, from U0 to U0 to U1, from this guy to this guy. And this inverse mapping f minus 1 is also C alpha. So when I have a C alpha diffeomorphism, not only I have this function f, let's put it this way, pushing U0 to U1, and that's a C alpha map. But I also have the opposite function, f minus 1 from U1 to U0, and that's also C alpha. And diffeomorphisms, they're important, for instance, when we talk about manifolds. I mean, they're important in many contexts. Basically, they mean that the differentiable structure, anything you can say about differentiability or anything like that, up to order alpha over U0 is preserved by the map F. But okay, so accept this definition for the time being. Let's note one thing that's always true, which is that if I have a C alpha bijection, right? So let's accept as important the question of whether there's a diffeomorphism between two open sets, whether a given f is a diffeomorphism. So if I have a C alpha bijection from U0 to U1, it could still be that it's not a diffeomorphism. It could be that there's going to be an inverse function, right? Because F is a bijection, so there's an inverse function in the set theoretic sense. But it could be that this inverse function is not differentiable, or not C alpha. But here's something that happens. If f is C alpha diffeomorphism, that is, if the inverse also has continuous derivatives to order alpha, then for all x in my domain, this should be x, the derivative of f at x is an invertible linear map from V to V. And actually, we're going to see that the inverse of this guy is related to the derivative of the inverse. Actually, let me not write that. Let me move on, right? Okay, how do we prove this? It's simply the chain rule. Remember, we are assuming that f is differentiable, and also that f minus 1 differentiable. After all, we have a C alpha diffeomorphism here. So when I compose f with f minus 1, I know I get the identity map in the domain of f, right? This right, it's over here. The identity map, but yeah. So if I do the opposite composition, I get this. So I can apply the chain rule, right? So this is just a restriction of a linear mapping from the whole of V to U0. So its derivative is the linear mapping itself, which in this case is the identity map. And here's what the chain rule gives me, right? So if I want to compute the derivative of a composition, right? So the derivative of f minus 1 composed with f at x. So how do I do that? Well, that's what's below, right? So df minus 1 applied to f of x, composed with the linear transformation df of x. So now I know that this guy times this guy is the identity. And I can repeat the reasoning in the other direction for any y in U, right? So this is for all x in U0. for all y in u1, I have the opposite. So df of f minus 1 of y composed with df minus 1 of y. That's the identity map over V as well. Now if I want to put these two things together, the best thing I can do is to take y to be f of x. Remember that f is a bijection, therefore for any y here, there's a preimage x here, a unique preimage actually. So, and then if I take y equals f of x, I see that above, right, so that if this is x and this is f of x, I see that above and below I have the same operators, just taking their product in opposite order, right? So I'm saying that if I take the product of this with this, that's the identity. If I take the product of this and this, that's the identity. Therefore, the operator dfx is invertible, and its inverse is given by this formula here. You compute the derivative of the inverse function at f of x, and that's going to be an invertible operator, so you take its inverse. So sorry, that's not, there's no minus 1 here. I'm just saying the inverse of dfx is this thing. Okay, and that's shown above, of course, right? I'm just saying that take the product of this guy and this guy in any order, you get always the identity mapping. Okay, so here, this is a necessary condition for a C alpha bijection to be a diffeomorphism, that the derivative operator at all points x is invertible. However, that's far from being a sufficient condition, and because I have the following. So is it, I mean, I can ask this question, right? So is it true that if I have a C alpha function between two sets and the derivative is always invertible, does it follow that this function is a diffeomorphism? Remember, in order for that to hold, you need the function to be a bijection, and you need it to be, you need it to have a alpha times differentiable inverse, and this derivative of the inverse of the order alpha has to be continuous. Now, everything breaks down if you consider the following simple example, which is basically parameterizing the plane by polar coordinates, right? So what is that? You take an r, that's a positive real number. You take a real number theta, and you map that to the point in the plane r cosine of theta, r sine of theta. So if you do that, you're parameterizing the plane by polar coordinates. But of course, this is not a bijection, right? Because this map is periodic in theta. If I add 2 pi to theta, I get the same values. So this map, like polar coordinates, cover the whole plane infinitely many times. Okay, so it's not a bijection. So there's no inverse function to speak of, let alone, I mean, there's no chance that it's going to be a diffeomorphism. However, you can compute its derivative. Well, it's going to be given to you by the Jacobian matrix. You know how to do it. If you do that, you find that the determinant of the derivative of f at x, right, of f, let me put it this way, r and theta at all points, that's just r, or actually r squared. Not that it makes a difference. The important thing for us is that r is non-zero. So, okay, why am I doing this? Well, the determinant in this case, I'm taking the determinant of this derivative. I mean, if I wanted to be more formal, I'd say, well, the derivative is represented by a matrix. This matrix is invertible if and only if its determinant is non-zero. And I've shown it to be invertible at all points by computing the determinant and saying, well, this determinant is equal to r squared, which is non-zero. So f has invertible derivatives at all points. However, it's not a bijection. Very far from it. Okay, what's the inverse function theorem? The inverse function theorem gives us a kind of a local converse. Saying, no, I mean, okay, so we've seen that if I have a C alpha function that is a bijection, then its derivative must be invertible at a point. So now suppose that I have a function that's C alpha, and it has invertible derivative at one point. So here's what this theorem says. If I have this, then there's an open set, an open neighborhood of x naught contained in U, so that's U0, such that if I look at the image of U0 under F, that's U1, well, that's another open set, and this function here, well, the restriction of F to U0, from U0 to U1, is a C alpha diffeomorphism. Somehow, okay, we just said that the fact that a function has invertible derivatives doesn't guarantee that it's a bijection, let alone that it's a diffeomorphism. But somehow locally that's true. So in the neighborhood of a point where the derivative is invertible, then the function is a diffeomorphism. Okay? So that's our goal for the next several slides for this video, is to start the proof of this theorem. It's a long proof, so I'm going to finish it in a second video. In this video, we're going to do kind of one step of the proof that's not too complicated, and another step that's a lot more complicated. And then at the end, so basically let me show you the steps, right? So first there's the issue of finding this open set, this U0, which is a neighborhood of x0, and that's going to be simple. It's just going to be a ball, and it's a ball where the derivative doesn't vary much. So all points have derivatives close to the f of x is 0. And now we're going to argue that restricted to this ball, we're not going to show that f is a diffeomorphism in one go. We're just going to argue first that, okay, I define u1 to be the image of u0, and then I'm going to show that f and its inverse are Lipschitz over this ball. So, okay, f is Lipschitz over this ball, and f minus 1 is Lipschitz. Okay, let me write this properly. F minus 1 is Lipschitz over this set, which I don't know if it's a ball or not. Now, that's all fine and good, but if I want to differentiate the inverse function, I have to show that u1 is also an open set. Well, that's part of the definition of diffeomorphism. It's even part of the definition of derivative, right? We always, when we differentiate functions in differentiate sense, we're always assuming that the domain is an open set. So showing that u1 is actually an open set is going to be a crucial step. And perhaps that's the kind of least obvious step in the proof. The hardest one, conceptually speaking. Right, and once we do that, then we're going to show that the inverse function is differentiable and actually C alpha. That's going to be in the next video. So step 3 is in the next video. Let's do 1 and 2, okay? And of course, I mean, here I'm being a bit loose, but I'm going to make this all much more precise. Okay, so notation for the remainder of the proof. Instead of writing df of x naught at all steps, I'm going to write t, right? So t is the derivative of f at point x naught. It's an inverted operation by assumption. Now, I'm going to look at this mapping that takes x to t minus 1 df of x. So the mapping from x to df of x is continuous because we're assuming that f is C alpha. Therefore, well, if alpha equals 1, that means that the first derivative is continuous. If alpha is larger than 1, then better still, right? It means that df is differentiable. Therefore, it's continuous. So x maps to df of x is continuous. Now, if I take a composition, if I multiply that by the linear transformation t minus 1, that's still continuous. Well, if you want, that's an exercise for you. But it's really easy. Well, really straightforward. Let me put it this way. So, okay, this is a continuous function from u to linear operators from v to v, which is sometimes read as L of v. And this function takes a value equal to the identity at the point x naught, right? So it's just saying, well, t minus 1 is defined to be df of x naught. So t is defined to be df of x naught. T minus 1 is the inverse of that, so the product here is the identity. Now, an easy consequence of that is that if you have a continuous function that's equal to the identity at a point, it must take a value that's close to the identity nearby points. Therefore, there exists an R greater than 0, such that for all x in this ball, well, I have to assume that this ball is also contained in U, right? So I can take a ball such that, sorry, another typo, t minus 1 df of x, the distance between that and the identity operator in the usual operator norm is less than a half. Well, less than or equal to a half, doesn't matter. So, and as noted before, this ball is my U0. So basically everything now happens inside this ball. I have this ball, it's convex, that's going to be useful pretty soon. It's convex, it's open. f is defined over this ball because the ball is contained in U, which is the domain of x, and the derivative of f of x is very close to t in the sense that t minus 1 df of x minus the identity is less than or equal to half in norm. Okay? Alright, so what about that? So now define this mapping, psi, I want to argue now that somehow, okay, I need a statement of this form, that if I look at f of x, that's very close to the linear approximation, right? So remember that t is a derivative, so f of x minus f of x0 should be close to t times x minus x0 for small, when the distance between x and x0 is small. But I need a very strong form of this. So I actually need something that like t minus 1 f of x or as f of x0 is very close to x minus x0. And I need something even stronger than that. I need that the distance between this, that this function is here is very close to the identity function somehow, or at least if you look at differences. Okay, so let me be more precise. So, that's sort of the intuition. Now define this function here, psi, that maps t to t minus 1 times f of x. This is well defined because, well, this is for any excellent element of v, this is a linear transformation from v to v, so everything here is fine. And my claim is that this function psi is very close, well, if you look at differences between psi's at different points, and you compare that to the difference between the 2 points, these two things are very close to one another in the following sense. That when the distance between x and x prime gets smaller and smaller, the distance between psi of x minus psi of x prime and x minus x prime, right, the difference between these two things, it gets even smaller, right? It's less than the distance between x and x prime over 2. Right, so how do you prove that? So now, it might be a bit mysterious why we need this, but it's just a way of saying that f of x is very closely approximated by its affine approximation given by a derivative. So, okay, let's accept that that's necessary for the time being. Okay, how do I prove this? So I need to prove something about values of a function, some kind of Lipschitz property for the values of a function f defined over u0, or sorry, not f, psi. So I need to do that, control psi or psi minus identity over u0, and I need to do that knowing that u0 is convex. So the good thing about convex mappings is that I can use the mean value inequality. So you can look at this as like x minus psi of x minus x prime minus psi of x prime. What's the derivative of that? Well, it's identity minus this derivative psi at point A. Right, maybe you have to think about it a little bit, but it's really not a problem. Right, you can say psi is a composition of f with a linear mapping, so you use the chain rule, and the fact the derivative of a linear mapping is the mapping itself. So, okay, what does the mean value inequality give us? Well, I'm looking at the differences between values of a function. I can say this is at most the distance between the 2 points where I'm computing the function, times the sup of the derivative over the line segment connecting x to x prime. Well, that's identity minus t minus 1, and in the last slide, we chose our ball u naught, right? So this segment is containing u naught by convexity. And we chose our ball so that this distance between identity and t minus 1 df a is less than or equal to a half. Therefore, we've shown that this difference here is less than x minus x prime v over 2, which is what we wanted to argue. Okay? So, okay, we have all these approximations, so what, right? So, well, first of all, notice that I have these two inequalities for psi of x, right? Just from the triangle inequality of subadditivity, right? So you see that the norm of psi of x minus psi of x prime, well, if I took the difference here, right? So I know that this difference has norm bounded by half times x minus x prime norm. But, and then I can just use, well, the triangle inequality to say, well, so then the distance between psi of x and psi of x prime is at most the distance between x minus x prime plus this half of the distance, which gives me the upper bound, and similarly I get the lower bound. Now here's a little exercise for you. Remember that psi of x is equal to t minus 1 f of x. So I claim you can show the following, that if I look at x, f of x itself, then not only it's a Lipschitz function, right? So it's control distance between f of x and f of x prime is a Lipschitz function. So, but also you have a kind of Lipschitz property from below, that the distance between f of x and f of x prime is at least x minus x prime distance times a constant. And these are the constants you get. I mean, the values of these constants are not really important for us. You see that I have norm of t here, norm of t minus 1. What's important is that this constant here is positive. This constant here is finite. And that we've shown f to be bi-Lipschitz. A bi-Lipschitz function is, by definition, a function that satisfies these two properties. And notice that such a function must be injective. If I take x different from x prime, then on this side I have the distance between x and x prime, and that's positive. So that means the following, that this function f restricted to u0, which is u0, is Lipschitz. And also that if I look at f restricted to u0 as a function from u0 to u1, that the inverse function is Lipschitz. So basically I get this from here. Well, I mean, I can say, what if I put f minus 1 of y minus f minus 1 of y prime here, and you see that you get y minus y prime. So you can prove also that the inverse function is Lipschitz. So there is the f is injective. So if I restrict the counter domain to be exactly the range, that's a bijection. And the inverse of this bijection is Lipschitz, right? So this is what u1 is going to be, right? Okay, so I have a Lipschitz function with a Lipschitz inverse. And that's all I've got so far. Well, that's already a lot, as you're going to see. But now comes a crucial step. I need to show that this image of u0 by f, the set u1, is an open set. And what do we need to prove that something is an open set? So here I have u0, just a ball around x0. And maybe this is y0 equal to f of x0. Let's say I have another point here, x1, and its image here, y1. Right, for any y1, this is u1. For any y1 in the image, I can find a pre-image here. Now, what do I need to show? I need to show that there's a small ball, a radius delta, around y1, such that any other point in this ball also has a pre-image. Perhaps a pre-image that's close to x1. Right, so I'm saying, okay, I need to show that u1 is open. I need to take an arbitrary point in u1. I need to prove that there exists a delta such that this whole ball was contained in u1, meaning for all y in this ball, there exists an x in u0 such that f of x is equal to y. Right, so that's what I mean. So all points in the ball around u1 are contained in f of u0 or u1. All the points around y1, they're also contained in u1, right? Then what does it mean to be in here? It means that you y is here if it has a pre-image in u0. So that's the challenge, right? So we don't know much about f, but somehow we need to prove that points have pre-images. I mean, by virtue of being close to points that have pre-images. It's sort of like that. How do we do this? Well, I mean, it's so we have to construct this pre-image. And what we're going to do is to transform that problem of finding pre-images into a problem about fixed points. And we're going to use Banach's fixed point theorem exactly in this step. How are we going to do this? Well, we need to remember Banach's fixed point theorem is about functions between complete metric spaces And here we're going to be looking at closed subsets of a Banach space. So this is closed. So therefore it's complete in the induced topology. So that's good. But here, so we're going to do this. We take y1 and u1, and that guy has a preimage, which is x1. And I take a ball of radius eta, closed ball of radius eta, call it f sub eta, so that this ball is contained in the open set U0. Of course, I can take eta positive here, because the U0 is open. And so now I have a ball around this guy that I know that's a preimage of y1. And this ball is entirely contained in U0. Okay, but I still haven't transformed a problem into a fixed point problem. Here's how you do it, okay? And it's kind of amazingly simple in some sense, but though it's a kind of a funny idea. So remember, my goal is to take a y that's closed, right? So in the end, we're going to take y in a ball of small radius around y1. And I show that y is also in the image of the function. It also has a preimage. And here's what I'm going to do. I define this function h. That's a function to which I will apply Banach's fixed point theorem. It's a function in principle defined overall f of eta to v. And it simply does this. It takes x to x plus, well, there's a funny looking thing here. T minus 1 y minus f of x. And of course, if I find an x here that's a fixed point of this function, that means that, well, x equals x plus t minus 1 y minus f of x. And that really means that y equals f of x. So fixed points of this function h are preimages of y. Of course, we expect to have only one preimage, right? So that will come in. So, okay, here's the claim. So remember I chose eta such that the ball of radius x1 is contained, right? So that's f of eta. And and this is contained in U0. And here's my claim. And remember that U1 I know belongs to y1 to u1. Sorry, y1 belongs to u1. And my claim is that if the distance between y and y1 is less than delta, which is this number here, then h has a fixed point, or the same, there exists an x in f eta such that f of x is equal to y. So if this condition is satisfied, this condition over here, then it means that y it has a preimage, and therefore it is in U1. Okay, this proof is going to have several steps, right? So we're gonna argue that h is kappa Lipschitz with kappa less than 1. Well, let's see why that is, right? So I want to compute h of x minus the h of x prime. Go back to the formula. If I'm going to have something like x minus x prime, I'm going to look at the difference. Y is going to cancel. I got to have here plus f of x prime. And sorry, where am I? I think I'm here. So that's going to be exactly x minus x prime minus t minus 1 f of x minus f of x prime. Now, this thing here is what psi of x minus psi of x prime, where I defined psi a long time ago. So I know that this thing here is less than a half times norm of x minus x prime. So h is kappa Lipschitz with kappa equal to a half. And that's good because that means the following, that if I can iterate age, I'm going to show that I can iterate age, then the Lipschitz constant goes very quickly to 0. So the composition of two functions, they're 1/2 Lipschitz is 1/4 Lipschitz. The composition of I functions, they're a half Lipschitz. They're the composition is 1/2 raised to I Lipschitz. That's easy to show. So we need to, okay. So I already know that it's Lipschitz, but that's not the only condition we're going to need, right? So we also know that, okay, if I take x belonging to f of n, I want to argue that when I iterate my map, it preserves f of eta. Remember that in order to apply the fixed point theorem, I need a function for a complete Banach space for a complete metric space to itself. So I'm going to argue that right now that this function is such that with my choice of constants, remember that here I'm assuming y minus y prime is less than a certain delta. And I'm going to argue that, that this is, that if I take this delta, then the set f of eta is preserved by age, is mapped into itself by age, and then I can apply fixed point. So, okay, how do I do this? Okay, here's how I do it. I just look at age of x minus age of x naught. So remember that f eta is just the ball of radius, x1, right? F of eta is just the ball of radius eta around x1. And then, well, okay, so I already know age is Lipschitz, right? So this is less than, or sorry, I want to show that age of x is close to x1. So I'm going to do that. So age of x is x minus x1. Okay, sorry. Just going to do it like this. Age of x minus age of x1 plus x1 minus age of x1. And let's compute these terms. Well, the first one we just showed that it's less than the distance between x minus x1 v over 2. The other one, well, age of x1, remember it's x minus something, x plus something, sorry. So this is exactly equal to t minus 1, y minus f of x1. Now, remember, this guy here is y1. F of x1 is y1. This distance here, if x belongs to the f of f eta, this is less or equal to eta. So everything is less than 8 over 2. Plus, let me just use the operator norm here. T minus 1 v, distance between y and y1. So what's the upshot of all this? I remember I fixed here, so that's my conclusion, which has been on the screen for a long time. I have y1 in u1, x1 is its preimage. I take eta such that this ball, this is f of eta, is contained in 0. Then any point in this ball of radius, well, exactly what I need, right? I'm taking this distance to be eta to norm t minus 1. If I have this, then I'm done. And why is that? Remember, I wanted to prove this property. And here's what I've shown, right? So how do I prove this? I need to know that the distance between age of x and x1 is less than or equal to eta. And this is what I have if I restrict to y that lies in this ball. Okay. And now, I've shown that, okay, that this distance is less than eta. So what do I have? I have a map age right? So I wrote here that H maps f of eta to itself, but actually I can just say, well, H maps f of eta to f of eta. Okay, great. I have a mapping from a complete metric space to itself, but I also have more, because I just argued that h of x minus h of x prime is less than a x minus x prime over 2. So all distances are contracted by a factor of a half by h. Therefore, if you iterate this, I mean, it's not hard to show that you have what I said before but didn't write down, which is that h to the I is 1 over 2i Lipschitz. So now you go back to Banach's fixed point theorem. Remember, you need the complete metric space, which we have. You need a mapping for that space itself, which we have. And you need the Lipschitz constants of the iterates to be summable. But, well, I mean, nothing could be more summable than 1 over 2 to the I, right? So we're in a good position to apply the theorem. And remember, that theorem guarantees the existence and uniqueness of a fixed point. In our case, we just need existence because we're just trying to prove that something is open. We're just trying to prove that y has a preimage. But since h has a fixed point, then it must be that y has a preimage. And we are done. Right? So, I mean, if you like, you could call this, I guess, h of y, and then you have y's all over the place. Now, the mapping depends on the y that you chose. But the point is that given y, you can define a mapping such that it has a fixed point. That fixed point is a preimage for y. As long as y is in this ball here, around y1. But that's good, right? Because it's basically saying the following. It's just saying, well, it's really saying that given an element of u1, I can find a ball of positive radius around the guy that's entirely contained in u1. That holds for any y1 in u1, therefore u1 is open. And that's what we needed to show. That's what we needed to show. And now, let me just recap and tell you what we have, and then we're going to stop and continue in the next video. So let me change the letters here because I see that I use different letters in the video. Here's what we have so far. We have f mapping u0 to u1. u1 is open. And we know that f is by Lipschitz when restricted to u0, meaning that it's Lipschitz above and also something like Lipschitz below. And that means that I've argued before, and now it says again as an exercise, that the inverse function of f must also be Lipschitz. Okay? Actually, I mean, the inverse function must be 1 over little f L Lipschitz. So what we need to finish the proof is to work from this and show that f minus 1 is a C alpha function. Okay, f restricted to u0 is a bijection because it's by Lipschitz. It's the inverse function is at least continuous, actually a little bit more, right? So it's 1 over L Lipschitz. Good. But we don't know yet that it's C alpha. Once we know, then we're done. Then f minus 1 is diffeomorphism. So notice that I'm going to be a bit cavalier in my notation. I'm going to forget this restriction to u0, pretend u0 is all there is, and then I'm just going to write this. Well, in reality, this should be this. And then we're going to argue that this inverse function has alpha derivatives. But that's in the next video. So thank you.